Hi, my name is Bahadur Ahmedov. Welcome to the course of multivariable calculus. In this video, we're going to solve a couple of problems from the online quiz on the partial derivatives and the directional derivatives. So in the first problem, we just need to find the partial derivatives of this functional with respect to the x and t. So let's find this with respect to the x first of all. So the partial derivative of the f with respect to the x is going to be equal. So the t is going to be considered as the constant. So basically e in the power of t is going to be just a constant. So that is why it is going to be here, e in the power of t times. Now we're going to take the derivative of this term, which depends on the x, which is going to be minus sine of pi x, right? So times to the derivative of the argument of the sine, which is going to be equal to the pi. So the partial derivative is going to be equal to the minus pi e to the power of minus t sine of pi x. So we can find the partial derivative of the f with respect to the t as well. So in this case, this term is going to be just considered as a constant. So that is why this is going to be left as a constant, pi x. So now we are going to take the derivative of the first term, which is e to the power of minus t. So the derivative of this term with respect to the t, it's going to be e to the power of minus t times the derivative of the minus t, which is equal to the minus 1. So it is going to be equal to the minus e to the power of minus t cosine of pi x. So let's consider another problem on the partial derivatives. So we've got another functional which is going to depend on the two variables x and y. We need to find its partial derivatives. First of all, I'm going to find its partial derivative with respect to the x. So for the simplicity, I'm going to rewrite this function in this form. So 1 over y times x and its derivative. So here y is going to be considered as the constant since we're taking the derivative with respect to the x. So that is why its derivative is going to be simply equal to the 1 over y. And whenever we would like to find the derivative of this functional with respect to the y, let me write this as a y in the power of minus 1 times x. So here we are going to look to the x as the constant. So it's going to be constant times the derivative of the y, which is going to be minus 1 times the y in the power of minus 2. So it is going to be equal to the minus x divided to the y in the square. So these two are the partial derivatives of this functional with respect to its two variables x and y. So we are going to use the partial derivatives in order to find, for example, the directional derivatives. So in this problem, we need to find the directional derivative of this given functional at this point in the angle pi over 6. So in order to find, so basically we are going to define the directional derivative of the functional in the direction of some unit vector u is equal to the dot product of the gradient of this functional, so the gradient vector, which is going to contain the partial derivatives of this functional, times to this vector u. So we need to first of all find all the ingredients of this formula. So the gradient of the f, or the nabla f, is going to be a vector which is containing the two partial derivatives of this functional. So we are going to find the partial derivative of this functional with respect to the x, first of all. So here we are going to look to the y, just a constant. So this is the constant, right? So the constant times constant is going to be rewritten as it is, and the derivative of the x cubed is 3x squared plus, so y cubed is a constant, and the derivative of the x squared is 4x in the power of 3. So now we are going to take the derivative of the y. Okay, so with respect to the y, so in this case x is going to be considered as a constant. So x cubed is going to be written as it is, and then the derivative of the y in the power of 4, which is 4y cubed, plus x in the power of 4 times 3y in the square. Okay, so we need to evaluate the gradient vector at this point 1 and 1, since we need the directional derivative at this point 1 and 1. So I'm just going to substitute x was the 1 and y was the 1 and evaluate everything. It's going to be 3 plus 4 And the second term is as well 4 plus 3, which is going to be equal simply 7 and 7. So now we need to find this vector u. So the unit vector, so in order to do this, let me draw the coordinate system. So this angle pi is given as, this angle theta is given as a pi over 6, right? So we need to figure out the vector in this direction, So in order to do this, I can make the triangle, right? I know the ratio of the opposite to the adjacent. Opposite is going to be, let's say, y to, opposite to the long side, the hypothenuses. Opposite to the hypothenuses is going to be equal to sine of this angle, right? So sine of this angle is going to be x divided to the y, let's say. So x or y divided to the x. Y divided to the x. Okay, so I know that this is equal to the 1 over 2, right? So since the theta is equal to the pi over 6, sine of pi over 6 is 1 over 2. So I can take the y to be equal to the 1 and x to be equal to the 2 simply. So basically, yeah. So that is why using this formula I can find, for example, this part. We can use the tangent, it appears. So the tangent of theta is going to be equal to the sine of theta divided to the cosine of theta, which is going to be 1 over t divided to the square root of 3 over t, which is going to be 1 over square root of 3, right? So the tangent of theta is equal to the y divided to the x. So from here, so this is equal to 1 divided to the square root of 3. So that is why y can be taken as 1 and x can be taken as the square root of 3. So this can be taken as the square root of 3. This can be taken as 1. So this is going to be the vector with the components square root of 3 and 1. So we need to find a unit vector in this direction. So the unit vector in the direction of this v vector, let's say, is going to be the v vector divided to the norm of this v vector. So the v vector has a component square root of 3 and 1, and the norm of this vector is going to be square root of 3 in a square, which is 3, plus 1 in a square, which is 1, which is going to be square root of 4, which is 2. So this is going to be square root of 3 over t and 1 over t. So what we are going to do is we just need to multiply this vector as a dot product to the gradient of this functional at this point 1 and 1. Right? So the directional derivative of this functional in the direction of the u is going to be the gradient of this function at this point 1 and 1 dot product to the u vector. So in this case it's going to be 7 and 7 times as a dot product to the square root of 3 over t, 1 over t, which is going to be equal to 7 square root of 3 over t plus 7 over 2. Nice. So in our last problem is again about the directional derivative. So we need to find a gradient of this function. So then we need to evaluate this at this point. Then we need to find the directional derivative in this direction of the u vector. So which is actually very similar to our previous example, right? The previous vector. So let's first of all find the gradient vector to this functional, so which is going to contain the t components, the partial derivatives of this functional with respect to the x and y. So the partial derivative of this functional with respect to the x is going to be, so we need to take the derivative of this function where y is going to be considered just a constant. So for example, tx plus k or c, so just a constant. So this is going to be the cosine of 2x plus 3y, so times the derivative of its argument with respect to the x, which is going to be t simply, because the derivative of the 3y with respect to the x is going to be simply 0. Right, so since this is considered as a constant here, so which is going to be t cosine of 3x, tx plus 3y. So now we need to evaluate the partial derivative of this function with respect to the y. It is going to be again the derivative of the sine, which is cosine, of 2x plus 3y. So now we need to take the derivative of its argument with respect to x, where x, with respect to the y, sorry, where x is going to be considered as a constant. So this is some constant plus 3y, so the derivative of a constant is going to be equal to the 0 plus derivative of the 3y is simply 3. So the answer is going to be 3 times cosine of 2x plus 3y. So now we need to find the directional derivative. In order to do this, at this point, it's minus 6 and 4. In order to do this, we need to evaluate the gradient at this point. So let's find the partial derivative of the f at this point, minus 6 and 4. It's going to be 2 times cosine of minus 12 plus 12, right? Which is equal to the cosine of 0 is simply 2. And the partial derivative of the f with respect to the y at this point, minus 6 and 4, is going to be equal to the 3 times cosine of minus 12 plus 12 is going to be equal to the 3, since cosine of 0 is equal to the 1. Good. So we need to find the directional derivative. So u vector is given as square root of 3 over t, right? Or sorry, I, square root of 3 times I, minus 1 over t j. So we can write this down as a square root of 3 over t minus 1 over t. So we can make sure that this is indeed the unit vector by just finding its norm. So the norm of this vector is going to be the norm in the square even. So it's going to be 3 over 4 plus the square root of 1 over t minus 1 over t is going to be 1 over 4, which is equal to the 1. So indeed it's a unit vector. So if I would like to find the directional derivative of this functional in this direction of the vector u, I just need to multiply the gradient vector of this functional at this point, minus 6 and 4, to use this vector as a dot product. So it's going to be the vector with the components 2 and 3 times the vector with the component square root of 3 over t minus 1 over t. And the dot product is going to be 2 times square root of 3 over t minus 3 times 1 over t. It's going to be square root of 3 minus 3 over t.